It's really great to speak today. So I'm Polina, and Pavel was also introduced. We are going to talk about how do we build neural networks that we can trust. And this will be a primer talk for Andrew's talk later today, which will be about generalization, Bayesian deep learning, and loss geometry. Okay, so recently there has been a lot of success in deep learning applications in various areas, such as search, chatbots, financial predictions, machine translations, and many others. However, it is still dangerous to apply deep learning as black box method for critical applications, where we not only care about accuracy and performance, but also about representing uncertainty. In particular, let's consider the problem of automated diagnosis. So we not only expect the model to perform well, but also faithfully represent the uncertainty in its predictions. So we would want to adapt this model to use in the human-in-the-loop manner in a way that the model outputs how certain it is in a particular prediction. And if the confidence is low, we would want to pass the decision-making to a human expert. And only if the model is very certain in a particular prediction, we would want to automate the process of medical decision-making. So in the next part of the talk, I will introduce Bayesian inference for machine learning, which is the framework for handling uncertainty in models. Let's consider a simple linear regression problem where we have the observed data on the plot shown with red crosses, and the dashed line is the true model that generated our data. So the targets are a linear transformation of the input x, and we have a single parameter in the model w, coefficient before the x, which we want to estimate. And we also have some observation noise epsilon, which is a Gaussian noise. In standard machine learning approach, we would want to find the setting of parameters w that would maximize the likelihood function of the observed data. In our case, it is Gaussian likelihood, and optimizing this function with respect to w is also equivalent to minimizing simple mean squared error between the observed target variables and the scaled inputs wx. After performing this optimization, we would find a single set of parameters w maximum likelihood, which is shown here with the red, with the green thick point. It's the minimum of this loss function or the maximum of the likelihood function. And it also corresponds to the thick green line over here on the plot. So we would, during the test time, go ahead and predict using this single set of parameters. And however, we can see that only observing 3 points here, we cannot be very sure that this is the function that generated our data. And we can imagine many perturbations of this function, which would be also very well explaining our observations. However, by only choosing to model our function with one parameters WML, we are discarding all of this information about uncertainty in our parameters. In Bayesian approach, we can work with this uncertainty, and we can infer distributions over our parameters instead. So as a first step, we introduce some prior distribution over our parameters w, which is shown on the left plot here. And it just reflects our prior knowledge about the parameters. And with different colors here, I showed the samples from the prior distribution, and they correspond to different linear functions here on the right plot. After we observe the data points, we may update our beliefs about W, and we compute posterior distribution of W given beta using Bayes rule. So in the Bayes rule formula, we have it's proportional to the likelihood of the data given a particular set of parameters times the prior belief about this set of parameters, also normalized by the marginal likelihood of our data. So here on the left plot, we see that the prior distribution was pretty much uninformative and very flat across the region of this values. And after we observed just a few data points, our posterior distribution is pretty well concentrated around the true value of the W. Indeed, after we observe more and more data, the posterior will be more and more concentrated around the true parameters. So after we see 9 data points, the variance of the posterior will decrease, and it will be more almost collapsed on the true maximum likelihood setting of parameters after we observe a lot of data points. So basically, the uncertainty in the model that we want to handle is coming from the fact that we don't have enough observations to be sure in our parameter estimate. And it's important to distinguish between 2 types of uncertainty. So there is epistemic uncertainty, or uncertainty in our model or parameters in our model. And it is coming from the fact, again, that we only have limited training data sets, and there could be many plausible solutions that explain our data well, as shown here on the top plot. There are many linear functions that could describe our observations pretty well. And there's also aleatoric uncertainty, which is our observation noise. So for a fixed model, we have some, for example, additive Gaussian noise that is often present in the data. And it's important to note that this aleatoric uncertainty, or uncertainty in the observations, can also be modeled in standard machine learning approach, in maximum likelihood approach, as the for example, we assume that our targets include some Gaussian noise, but this epistemic uncertainty or model uncertainty is what we get from taking Bayesian approach when inferring our parameters. So the total predictive uncertainty that we have when we combine both uncertainties is additive of the epistemic and aleatoric uncertainty. And yeah, it's another example that is showing how epistemic uncertainty behaves is this nonlinear model, which is a more realistic scenario. For example, for deep neural networks, we have highly nonlinear transformations and highly nonlinear models. So the epistemic uncertainty is growing in the regions where we don't have any observations, and it's so the model is usually more certain in the regions where we have observed data, and it's growing in between data as well as at the extrapolation region. Okay, so after we computed our posterior distribution P of W given data, we can use it to make predictions in the procedure called Bayesian model averaging. So when we have a new data point x star, we will compute the posterior predictive distribution, marginalizing over all possible setting of parameters W with respect to how probable they are in terms of the posterior distribution. And actually, when we take maximum likelihood approach, it will be the special case of this integration where the posterior is only delta function in a single set of parameters, W maximum likelihood. And then we will be discarding all of the epistemic uncertainty that we get when we don't observe a lot of data points. So ignoring this uncertainty in the posterior leads to overconfident predictions because we are betting all of our belief into only a single set of parameters W. So let's maybe talk in more detail what overconfidence means and why it matters. So let's consider a classification problem in medical imaging where we get some data from the patients and we have a deep learning model that predicts that either the patient is healthy or unhealthy. And the output of the network are these confidences, softmax probabilities, but they cannot be treated as the real meaningful probabilities of a particular data point belonging to a particular class. So for a well-calibrated model, we would expect that for all of the data points that the neural network predicted to be healthy with 80% probability, we want it to be correct in roughly 80% cases. So in this example, we have 5 medical images, and for all of those we predicted 80% probability of being healthy, and we are correct in 4 out of 5 examples, so it's roughly 80%. However, in practice, deep neural networks are extremely overconfident, and this P of W given X, softmax probabilities, are not the actual probabilities of belonging to a particular class. And this may be very dangerous in the case of the example I talked about in the beginning. When we have automated diagnosis, if the model cannot signal about it's not being able to make a reliable prediction, we cannot fully trust it in the decision making when the mistakes are very costly. The measure of how well the model is calibrated is this expected calibration error. So let's discuss how it's computed. So we take our model and all of its predictions on the whole data set, and then for all the confidences that it outputs, we bin these confidences from the region from the point, like whatever the lowest confidence is, to up to 1. And then for a particular bin, let's say for the bin where we have all the inputs that have prediction confidence between 0.6 and 0.7, we expect the accuracy to be somewhat between 0.6 and 0.7. And that would reflect the confidence of the model, and that would connect the confidence of the model and the actual accuracy on that subset of the data. And this gap shown in red bins is what is the calibration gap between the perfectly calibrated model, which is the diagonal, and the like real model neural network, which is shown with the blue bins. And so the model on the left here is very poorly calibrated, whereas the model on the right is outputting meaningful probabilities and confidences. And so the expected calibration error is this cumulative sum of all these gaps across all of the neural network's predictions. And ideally, we want it to be low. So for like all of the problems that I mentioned up to this point, we want to somehow incorporate uncertainty in the model, or epistemic uncertainty in our deep learning models. So instead of having some values for parameters after training, we would have a posterior distribution over all the parameters in the neural network. And this, in theory, would lead to better predictions and well-calibrated uncertainty estimates. But the challenge here is that usually modern neural network architectures have millions of parameters, and in the posterior distribution formula we have this normalization constant, and it's so if the W is million dimensional, we cannot tractably compute this integral because of the complicated nature of the neural network function, and also we cannot numerically approximate it. So we have to resort to some approximate inference techniques to find this approximate posterior distribution over parameters of deep neural network. So there are various families of approaches. The most popular ones are Laplace approximation, variational inference, Markov chain, Monte Carlo, and our group is working on geometrically inspired approximate Bayesian inference. This will be more discussed in Pavel's part of the talk and seminar by Andrew. And I will just briefly introduce the three first approaches mentioned here. So in Laplace approximation, we want to, our posterior distribution is some really complicated distribution. It's probably a multimodal, and it may not belong to any of the standard families. So in the Laplace approximation, we want to approximate one of the modes of the posterior with a Gaussian distribution. So what we do is we take maximum a posteriori solution, so the peak of one of the modes, and place our Gaussian approximation here, which is shown in green. And we use the information about the local curvature close to this maximum a posteriori solution to fit this Gaussian approximation. So the problem here is that first it only captures a single mode, and we discarded all the information about probability mass here. And the second moment of this Gaussian distribution, to compute it, we need to calculate the second derivative of our posterior distribution, which can be pretty computationally extensive in exhaustive in the case of million-dimensional neural networks. Another family of approximate inference approaches is variational inference. In this technique, we want to define some family of distributions which will be approximating our posterior. And within that family, we are looking for the best approximation in terms of some distance between distributions. So there's this scale divergence measure of how similar distributions are. And we can minimize it with respect to the parameters of the approximate posterior. And we find, in the case of Gaussian approximation, the best mean and covariance matrix that describe this distribution. So in the case of minimizing the KLQP, so it's not symmetric, so it has different properties whether we minimize it in this way or the reverse way. And in this case, we expect the Gaussian approximation to roughly cover one of the modes as well. Another branch of popular approach is Markov chain Monte Carlo. And so I won't go into much detail about it, but instead of fitting some closed form approximation, we just want to build an algorithm to approximately sample from our posterior. So instead of having some distribution approximation here, what we get from this approximate inference method is the samples, Markov-Chain Monte Carlo samples that are coming from our posterior. And in case of deep neural networks, in practice, what this procedure involves is modifying stochastic gradient descent in some way that we would expect to see to get samples from the posterior. So all of these approximate inference techniques that I mentioned, they don't take into account the geometry of our posterior and the shape of our posterior. And these can, in fact, contain a lot of useful information and inspire new approximate inference techniques for better approximating our true posterior distribution. So in the next part of the talk, Pavel will be focusing on how we use this information about loss geometry to build new approximate inference algorithms.
So thank you, Polina. So I'm Pavel. I'll be presenting the second part of this talk, which will be about loss surfaces of neural networks. And just first of all, maybe let's fix what we mean by loss surfaces. So typically our networks, they're just models that have parameters, W, similarly to the linear models that Polina discussed. And these parameters live in a very high...
You wrote really big, actually.
Okay. So typically these parameters, they live in a very high dimensional space, like 10 to the power of 6. And to train the networks, we are just minimizing a loss function. So a loss function for a fixed data set would be just a function of the parameters. So it's just this million dimensional function. And we are trying to find its minimum. And that way we find the weights of the network. And in this part of the talk, we'll try to say something about the geometric properties of this function, loss of W. And one important thing to mention is that typically the loss is very much related to the posterior density. So the loss is usually our likelihood of the data, P of W, given the parameters of the network, logarithm of that, plus some regularizer on the weights. And this regularizer you can think of as just logarithm of a prior on the weights. And then this whole thing becomes just logarithm of the numerator in the Bayes rule. So logarithm of the product of the likelihood term and the prior. And this connection, it's actually really important. Yeah.
So this means that your choice of regularizer and loss function, in order to be a meaningful posterior, has to be normalizable, correct?
This thing is not normalizable, right? This is this thing is not normalized, but for many regularizers it will be normalizable, but it's not really essential for this part of the talk and for the whole discussion. Like,
how is it a posterior distribution if it's not normalizable?
Mm-hmm. So this is just like the connection between the posterior and the loss. So if it is normalizable, then you can say that the loss is just the logarithm of your posterior density up to a constant. But if it isn't, you can still like talk about the properties of this loss function of W, and this discussion will still make sense. But I guess I wanted to mention this to build the connection between the loss functions and the posterior density to say why it's important to understand the loss geometry in order to do approximate inference, which we'll get to soon. So yeah, this is what we mean by loss surfaces. We'll just try to talk about the geometric properties of this function loss.
Negative? Just a negative.
Oh, sorry. Yeah. It's this is the minus the loss function because we want to minimize the loss function, and that means we want to maximize the posterior log density. Yeah. Why do we care about loss surfaces? So first of all, as I said, it's very much related to the posterior density. And if we want to try to approximate the posterior, so as Polina said, we usually cannot actually compute the posterior. And especially in neural nets, it's pretty much impossible. And we usually come up with some way to approximate the posterior. And often the way we do this for neural networks doesn't take into account the actual geometry of the posterior. It's very, very ad hoc. We just try to fit some kind of a Gaussian around a given solution. But if we better understand the geometry of the posterior, we can build better approximations. But except for that, we can just think about loss surfaces, like analyzing loss surfaces as a way of understanding something about our solutions. So, for example, certain properties, so certain geometric properties of the solutions in the weight space can be related to the generalization properties of the neural network. So there is this concept of flatness, which we will discuss later. And if it's conjectured, at least, that if a solution is flat in the weight space, then the network corresponding to that solution will generalize better. And like if we understand the connections between geometric properties and generalization, we can try to develop new training methods that are promoting the geometric properties that we want from our solutions. So let's start by looking at some visualizations of loss surfaces to build more intuition. And we'll have a lot of these visualizations in my part of the talk. And so how do we actually visualize a loss surface? Because it's a function, like the loss is a function of a million different parameters. But we cannot look at a million parameters at the same time. So what we do is we just pick a two-dimensional subspace of the parameters. So imagine this is a million-dimensional parameter space, and we pick just pick some 3 different points in this million dimensions. And then there exists a unique plane, like a fine subspace, that passes through the 3 points. So this is our plane S, and then we can try to restrict our loss surface to this plane. So, for example, if these 3 points are W1, W2, and W3, then we can parameterize any point in this surface as any point in this plane as alpha1 W1 plus alpha2 W2 plus alpha3 W3, where alphas sum up to 1. So they don't have to be positive, but they have to sum up to 1. And then that would give you any point in this two-dimensional plane. And we can express any two-dimensional plane in the parameter space like this. And then we can try to visualize the loss as a function of a point only in this two-dimensional subspace. So here, for example, in the slide, you can see this type of visualization done by our friend Javier Idiami. And you can find more of this on his website. They're very cool. And so to make these visualizations in particular, what he does is he runs SGD. So the standard training of neural networks, he gets some point W in the weight space, some solution. And then he just picks 2 random directions. So W plus D1 and W plus D2. And then he uses these 3 points to define this two-dimensional subspace. And then you can visualize the loss surface around the solution when you look in random directions. And you see this type of behavior. So this the minimum is down there, and then you can see how the loss grows as you move away from the minimum. And you can actually make these visualizations for different hyperparameters in your network and try to understand how the hyperparameters affect the geometry. And here he fixes all of the architecture and most of the hyperparameters of training the same for all the plots, but then he varies like one hyperparameter at a time, and he looks at how the loss landscape changes. And you can see that you can actually get some intuition from just looking at these pictures about what the hyperparameter does. And let's look at this example more closely. And this was first noted in a paper called Visualizing the Loss Landscape of Neural Networks by Tom Goldstein's group. And here, again, everything is held fixed. So this is a ResNet network, some network. And the only difference is that in this part they removed the so-called skip connection. So so there is a small architectural difference between the networks that you see here and the networks that you see here. And even without knowing, even if you don't know what the skip connections are, just looking at these plots, you can see that the loss landscape here looks more smooth and easier to navigate for optimization methods. So it seems like if we ran SGD on this landscape, it might be easier for it to find the minimum than if we ran it here. And it actually turns out that in practice, it's much easier to optimize deep networks with skip connections than without. So this is an example of how we can build intuition about certain like architectural choices or other hyperparameters of our networks by looking at visualizations. So this is the next part of the talk, and just looking at visualizations like this, we only usually see one local optimum in the loss landscape. But this is because we are only restricted to looking at two-dimensional subspaces, and in reality there are like millions or much more than that of local optima for neural networks. They are very, very multimodal. And one way to see this is if you run your training, so you run this minimization here several times from different random initializations, you always get different solutions. And for example, here we ran this minimization 3 times, and we got 3 different solutions. And then, so W1, W2, and W3, and then we did that type of visualization in the plane containing 3 different solutions. And if you do that, you get a landscape that looks just like this. So you just see 3 of these wells of low loss. And in between them, there are regions of very high loss. So if you just directly go from one solution to the other, the loss increases a lot. Like a point here is completely useless for classification. For the problems that we are trying to solve, it doesn't do any better than a randomly initialized network. But what we found is that in our work with Andrew and Timur, who is here in the audience actually, that this is just because of the way we are visualizing. So it's possible to find connections between different modes such that the loss remains very low along the connections. So here, if we just take these 2 points, we can find a different plane of the loss landscape in which the picture looks more like this. So you can travel from one of the modes to the other mode without leaving the region of low loss. So you can go just always staying in the region of local optima. So pretty much, it kind of says that at least many of the local optima in neural networks are connected to each other. They form a connected set, and you can travel between them without going through barriers of high loss. And actually, these connections between different modes, they can be made very simple, and it's kind of easy to find them. Like, not much more complicated than just finding the solutions themselves. So, yeah, the connections, they can be planar, so they can lie, this paths, they can just lie in one two-dimensional plane of this million-dimensional space, and they can be of the shape, of this form, like polygonal chain with just one bend, or this quadratic Bezier curve. And Andrew will talk in more detail about how exactly you can find these paths. And recently we made some more visualizations, like it's the same type of visualization as here, but in higher definition. And we made this together with Javier and Timur. And you can see that, yes, this is the same type of visualization. So we have our optima here. They have low values of the loss, and then as you move away as you move along the curve, the loss remains very low, but as you move away, the loss blows up. And if you try to go directly from this solution to this solution, you would go over this spike of very high loss. So you have to move along some curve to find this path of low loss. Okay, and this is another visualization of the same thing, but from a different perspective. And now I wanted to reiterate on the connection with Bayesian inference. So as we mentioned already, it's important to understand the geometry, and in particular, as we now discussed, the landscape of the posterior, or the shape of the posterior, actually kind of looks like this, at least in some subspaces. And the most basic technique for approximate inference in neural networks is this variational inference with Gaussian approximation that has an independent Gaussian for each of the weights of your network. And if you just did that for this type of posterior geometry, you would only be able to capture a really small part of the posterior. But we actually want to cover, the more mass of the posterior we cover, the better. And this means, this kind of motivates why we want to take the geometry into account when we try to come up with new approximate inference techniques. So yeah, so there are many practical implications of mod connectivity that Andrew will talk more about in his talk. But now let's, because we are short on time, really quickly talk about this last thing called flatness. So as I said, the solutions, the way we train neural networks is by optimizing this loss function, and we get a minimum of the loss function, and we can talk about how flat the minimum is. So for example, for this green function here, we would call this minimum flat or wide, and this minimum sharp. Just intuitively, this is not a formal, there is no formal definition that's accepted by everyone in the community, but there is just this intuition that there are wide optima and sharp optima. And there is a conjecture that wide optima correspond to networks that have better generalization properties than networks that correspond to sharp solutions in the loss landscape. And one of the intuitive reasons for that is that the train loss surface, shown in green here, and test error surface. So we train the network by minimizing the loss on our train data, and we test it on a different data set. And the shape of the train loss that we use to train the network and the test error, which we actually care about, are probably similar, but they might be shifted with respect to each other. And if they're just shifted horizontally, like you see here on the slide, then the wide minimum, it wouldn't be as affected as much by the shift as the sharp minimum. And so this is one of the intuitions for why we might think that wide optima are better than sharp optima. And there is another argument based on the idea of margin. So the idea here is that, so just let's look at this visualization first. We have a classification problem of this Swiss roll dataset. So there are two of the spiral parts of the dataset, each corresponds to its own class. And we can build two classifiers, the one here and the one here. They both have 100% accuracy on the train data that we show it, but they have different generalization properties. And one reason for that is that this classifier has a larger margin. So if you look at the decision boundary between the classes, you need to move it further to break classification than here, because here the decision boundary passes really close to the data points. And you can connect this idea of margin to the flatness again. So our solution, so these are actually visualizations of the loss surface around this solution and this solution. And these are from the paper Understanding Generalization Through Visualization by Tom Goldstein's group. And what you can see here, so this network responds to like the center of this volley of low loss. And as you move the point away from the solution, the loss doesn't increase very quickly. So moving the point away in the loss surface corresponds to perturbing the decision boundary. So you cannot, in order to break the classification on train, you have to move your weights quite far. While here, you actually just move your weights by a little bit and you break the predictions completely. And that means that in this case, you would have larger margin for your decision boundary. And you can also connect this to, you can also try to reason about flatness from the Bayesian perspective. So in Bayesian machine learning, there is this framework of model selection. So when you have different models, you select a model that has the highest marginal likelihood or evidence, which is actually the denominator in the Bayes rule. So it's the integral of the, it's equal to the like probability or how likely it is to generate your data from the prior of the model. So it's equal to the integral of the likelihood times the prior over W. And it turns out that you can select the model that has the highest marginal likelihood, so the highest likelihood, the highest value of this integral. And if we make some very crude approximations, we can try to connect the marginal, like the value of the marginal likelihood to the width of the corresponding solution. So here we can try to approximate this integral with just assuming that the shape of this function under the integral is rectangular. So assuming that it just has the height equal to the maximum value of the function under the integral and has a certain width sigma w given d. And then the height of the function is the value of the function attained at the maximum a posteriori solution. So if you maximize this function, you get WMP. So you just substitute WMP into the function, and you get this value as the height of your function under the integral. And then we assume it has a certain width sigma, and then you just can approximate the whole integral as the product between the height and the width. And so it means that for a fixed height, so if our model, we have two different solutions that correspond to the same value of the loss. So they have this similar values for the product of our prior and likelihood, or like regularizer and the loss. Then we would prefer the solution that has a wider, corresponds to a wider optimum. And yeah, so the conclusion is that you can argue that you want wider optima and that wider optima would generalize better. And we use this intuition to motivate a method called stochastic weight averaging, or SWA. And Andrew will talk about it in great detail. But the high-level idea is that it kind of implicitly promotes width. And it turns out that doing so actually improves generalization in practical applications of neural networks. Yeah, and because we have no time, let's skip this slide. And the last thing I wanted to show you is that it turns out that the loss surfaces are actually probably more complicated than you might think. So it's actually possible to find these two-dimensional subspaces of the parameter space in which the loss landscape looks like any picture, like anything you want, pretty much. So there is this paper, Loss Landscape Sightseeing, and they used a similar approach to what we did for the connecting different optima, and they were able to find two-dimensional planes in which the loss landscape looks like the pumpkin, Halloween pumpkin, and anything, basically like any pictures. So the conclusion, I guess, is that there is still a lot to understand about loss surfaces, and they are very complex objects. They live in this million-dimensional space, and they're non-convex, and they have like millions and millions of local optima. But yeah, so it's really important to try and understand more about them for the reasons that we discussed, for better Bayesian inference and better training methods, and just for better understanding of generalization in deep learning. So yeah, that concludes the talk. This is another visualization of the mod connectivity.
Great to be here. Thanks, Ray and John, for organizing, and Molly, and Pavel and Polina for starting off the talk. I'm going to continue talking about loss values, generalization, and uncertainty representation, and efficient approaches to Bayesian inference in modern deep learning. So I'll start with just a pattern recognition question. So let's suppose we have these data points, airline passenger numbers indexed by time, recorded monthly. And we want to make predictions far into the future. So we want to predict airline passenger numbers, in this case in 1961. And we've got three model classes we're going to consider. A straight line, a cubic polynomial in choice 2, and a 10,000th order polynomial in choice 3. So I'd like you to do sort of a show of hands, say which choice will you go with. So how many people vote for choice 1 here? Okay, choice 2. Couple, don't be shy. Sometimes it's like 80% choice 2, other times 80% choice 1. Choice 3? Okay. I hope I didn't bias you. Because actually, I would argue for choice 3. And I think choice 3 is unsatisfactory because we know that probably none of these choices describes the ground truth generative process for these observations, but at least we'll be able to get closer to that ground truth through some setting of the coefficients in choice 3 than we could with choices 1 or 2. And in fact, choices 1 and 2 are special cases of choice 3. And for the same reason, actually, choice 3 is unsatisfactory because it's only a 10,000th order polynomial. We would actually want an infinite order polynomial if we could manage it, and even that is really not as flexible as we would like. And in fact, we would see that this kind of inclination is starting to appear a bit in practice. We don't think about it very explicitly, but we're using neural nets with 30 million parameters for problems with 50,000 data points and finding that we get very good generalization. And actually, there's some beautiful arguments in Radford Neal's 1996 PhD thesis on Bayesian neural networks in favor of basically embracing complexity, choosing the most flexible possible model you can imagine because you at least are being optimistic. You're really trying to find sort of a truth. Well, at the same time, not overfitting because we're not learning these parameters through maximum likelihood. We're considering a different procedure to set these parameters. So that's basically how we resolve this paradox and embrace the flexible model without overfitting. I imagine many people who went with choice 1 would assume we missed some interesting structure like seasonal effects and things like this in the data, but we don't want to overfit. There was also an interesting example in that thesis about character recognition that was arguing that no matter how flexible our model is, there's probably something we can add to it to get just at least a bit better performance, like accounting for irregular writing styles or weird ink blots or things like that, on the page. So some of you may have seen this cartoon from XKCD. It sort of was quite popular a few years ago. You have two people talking to each other. One says, this neutrino detector measures whether the sun has gone nova. Other person says, then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells the truth. First person says, let's try. Detector, has the sun gone nova? We hear the dice rolling. The detector says, yes. And one of the people says, well, the probability of this result happening by chance is 1 over 36, 1/6 squared. That's a p-value less than 0.05, so I conclude with statistical significance that the sun has exploded. Other person says, bet you $50 it hasn't. So different people in different areas have different reactions to this cartoon. If you ask a game theorist, they'd say, why only $50, right? Because if the sun has exploded, you can't lose anything more. So it's like the logical thing to do is bet everything you own. So from the Bayesian perspective here, I mean, we have a lot of prior experience, waking up and seeing the sun rising. We've probably played a number of board games before and rolled 2 6s. A priori, it seems significantly more likely that this result is from noise, basically, than the sun has actually exploded. And if you feel like procrastinating, you can compute the ratio of posterior odds for each of these 2 hypotheses. We have hypothesis 1, sun has exploded. Hypothesis 2, sun hasn't exploded. What we really want is, the posterior probability that it's exploded, given what we observed, that the detector has said, yes, it's exploded, over the posterior probability that it hasn't. So this is a ratio of marginal likelihoods that Pavel was talking about at the end of his talk, times a ratio of prior odds. And using very conservative estimates, we can basically lower bound the relative probability that it hasn't exploded, or that it has exploded, or that it hasn't exploded over that it has exploded by something like 40 trillion. And this would just be, given what we know about stars and, supernova and things like this. So we ought to sort of use our prior knowledge in doing hypothesis testing, but it goes beyond that. Actually, David Mackay, in his information theory textbook in chapter 28, argues that even in a lot of cases, if our ratio of prior odds is equal, the marginal likelihood, the d given h terms here, will still automatically favor the simplest explanation that's consistent with our observations. And that's also how we resolve that seeming paradox on the first slide, how we can embrace a flexible model class and still not overfit. We don't want to say that solutions that we actually believe are a priori possible are actually impossible in our modeling procedure, because then we're just not being honest in the way that we're modeling the data. But we also need to think about which solutions are a priori likely. So there's this interesting plot in that information theory book where on the vertical axis you have the evidence, on the horizontal axis you have this sort of conceptualization of all possible data sets. And from this perspective, generalization isn't just a one-dimensional concept associated with the flexibility of a model, but it's more associated with which solutions you can represent a priori, which you would want to be as broad as possible, at least in the sense of representing anything that you think has even epsilon probability of being true, but also the distribution of that support. And that sort of says, well, which solutions do you think are a priori likely? And even if you have sort of an equal sort of prior odds for various different hypotheses given a particular data set, the evidence will favor a model of appropriate complexity. And so this is to kind of explain the kind of Occam's razor effect that's happening underneath Bayesian inference. And Pavel alluded to that briefly with that Occam factor term in the marginal likelihood. Okay, so just as a brief review from the primer, in order to form our predictive distribution, what we ultimately want to use to make predictions with a Bayesian approach, we compute the integral of our predictive distribution given a set of parameters, and then we weight that by the posterior distribution over those parameters given the data, and then we integrate over all possible settings of the parameters. So in words, what that's saying is that we don't want to use a single setting of parameters to make predictions. We actually want to use all possible settings of those parameters, and we want to weight all of those by their posterior probabilities. This isn't really a controversial equation. This is just an expression of the sum and product rules of probability, and this is the predictive distribution that we ultimately want to use. So if we are betting everything on just a single model, we're ignoring all of the uncertainty in this posterior. So we shouldn't be surprised if our predictions are then overconfident, because we're just throwing away a lot of uncertainty information that we ought to be representing in our model. And that's fundamentally why we actually see miscalibration in neural networks. So the challenge in working with this approach is that this integral often isn't tractable. So in some cases, it is, like if you use a Gaussian process regression model, quite amazingly, you have both a very flexible approach and a completely analytic approach where you can write down the predictive distribution in closed form. And in that sense, there isn't even really training. Like you just have your prior model, you can write down your likelihood mathematically, and you can write down the exact equation that you want to use to make your predictions. There's no like waiting for SGD to converge or anything like that. But in many cases, we can't do that. We can't do that with neural networks. We have a nonlinear transformation of the parameters inside this distribution. Our posterior overweights will be very non-Gaussian. And so we have to resort to some kind of approximate inference. And the challenge in the context of modern deep learning has been that the parameter space is extraordinarily high dimensional. So I mentioned maybe like 30 million dimensional would be common. So even though Radford Neal in the mid-90s during the second wave of neural nets actually managed to make Bayesian neural nets work better than any other approach, so they were winning all of the competitions at the time, we can't just directly recycle the MCMC inference procedures that were in his thesis because they simply wouldn't scale to these sizes of models. And there are also a lot of other subtle effects like the connection between wide solutions and generalization that we might want to consider when we're following a Bayesian approach to approximating this integral. Fortunately, though, there's been a huge amount of progress just in the last year. So I think that a lot of these methods aren't just kind of relevant to what a lot of people are doing, they're newly relevant. So I think in the last year we've seen a number of papers reporting Bayesian inference results at ImageNet scale with modern deep learning procedures. And so a lot is really changing in this space. And I would say Bayesian methods have gone from impractical to quite practical just in that sort of short period of time. And a lot of the research in my group is essentially figuring out how to not do variational inference to evaluate this integral. Instead, think about things like recycling information in the SGD trajectory in order to do efficient Bayesian model averaging. Okay, so I've already kind of said most of these points. I gave a talk at a deep learning summer school, and I kind of enumerated some of the pros and cons of Bayesian methods in deep learning. So it's a powerful framework for model construction and understanding generalization. As Pavel mentioned, we could start to rigorously understand why, for example, wide solutions might generalize better from a Bayesian perspective. We get natural uncertainty representation and calibration. In the real world, we want to make decisions with our models. We don't just want like good accuracy on ImageNet or CFAR 10, and you might even argue from a philosophical perspective, if your approach could never be used to make a decision, is it ever going to have any kind of practical impact? I think an underappreciated or maybe a point that is maybe even not that well understood or known is that Bayesian methods can also lead to much better point predictions. It's not just about better error bars on your predictions, it's about better predictions. It's a different mechanism for arriving at our predictive distribution. And in fact, I would say this difference between marginalization, that is integrating away the posterior, and optimization is the key difference between a Bayesian and a non-Bayesian approach. Most people think it's about the prior. I think it's about integration versus optimization. We can interpretively incorporate prior knowledge and domain expertise. It's been successful before. And a lot of things about neural nets that seem mysterious, like more parameters than data points and so on, actually start to become quite understandable when we view them from a probabilistic perspective. Why not? Has been computationally intractable in the past. Can be quite complicated, so sometimes you might be doing a lot of extra stuff on top of regular SGD training, but I would say that this is also changing. A lot of the approaches that we'll discuss in this talk are actually quite simple and will get you both better point predictions and better calibration and, in regression, predictive distributions. Okay, so a few years ago, when I was faculty at Cornell, Jorge Nosadal, one of the creators of LBFGS, came and gave a talk, and he was trying to explain why mini-batch SGD methods seem to be doing better in deep learning than his LBFGS methods and other kind of quasi-Newton full-batch approaches. And this was quite a key question, especially then, because SGD seems like one of the worst possible optimization procedures compared to what else we could be using in theory. Yet it is the preferred method for training neural nets and SGD variants like Atom. And so this was one of the early insights as to why SGD might generalize better, that it actually found these wider basins of attraction almost because it's not able to find the sharp optima. It's like so bad it can only find wide optima. And here we have this just conceptualization on the horizontal axis of like different settings of the neural network parameters. On the vertical axis, we have the loss that we're minimizing to learn those parameters. The idea is that there's this shift between the training loss in black and the testing loss in dashed red. And for that reason, the flat minima won't have so bad testing loss, but the sharp minima might have very bad testing loss. And I think this shift is actually very intuitive because, let's suppose you add or removed a few points from your training set. You'd probably be quite alarmed if you didn't learn a new setting of the parameters. Even if the training and test points are from exactly the same distribution, if you have a limited sample of each, you wouldn't expect your model to be fully specified by what you've seen. And if it is, then that actually could be a red flag. So this shift is something that should actually always happen in practice, and if it doesn't, you might be worried. In terms of whether this width is sort of interpretable, so there have been some papers that argue that you can reparameterize and give the appearance of width. And so maybe we shouldn't put too much stock in this concept of width and how it relates to generalization. In response to that, I would say that typically when we're working with a model, we're not suddenly reparameterizing it and then comparing, maybe different basins of attraction corresponding to different parameterizations of the model. So I would say in practice, this isn't something we encounter very much. Another thing I would say is when you reparameterize and get the appearance of width, then the different points here actually correspond to the same solutions. And so, of course, in that case, this shift argument won't really make very much sense because a peripheral point is the same answer as a central point, so it shouldn't be worse than the central point for generalization. This argument holds when different points in weight space here actually correspond to different functions, different models. And if that's the case, then actually everything that Nosadal was saying about optimization seemed to be great motivation for following a Bayesian approach in deep learning. Because if these wide areas of the loss surface actually existed and they actually meant something in the sense of different parameters giving rise to different functions, then integration should give us a very different answer than optimization, because now we're including all of these really good models in our predictive distribution instead of just one of them. So it seemed like Bayesian methods weren't just sort of promising in deep learning for the reasons I've already mentioned, but especially promising for these types of models because you have these very strange loss surfaces. And if you think about it, the shape of the loss surface ought to matter the most for a Bayesian approach rather than for an optimization procedure where you're just trying to find a single setting of the parameters that optimizes the loss. If you're integrating, you actually really care about the specifics of the shape. Okay, so this was kind of great motivation for trying to take up Bayesian deep learning. And a good starting point is to further understand the geometric properties of these loss surfaces, which are, as Pavel mentioned, are closely related to the posterior distribution over the parameters that we're trying to estimate. So if we just initialize with 3 different settings of parameters for our neural network and train SGD to convergence, quite often we have what appear to be isolated local optima. So this was kind of the standard intuition. And indeed, if you try walking on a straight line from any one point to the other, you incur typically very, very high loss. And this had been recognized in a number of papers. Just to recap, this is a visualization of actually a very high dimensional loss surface formed by a linear combination at any given point of these 3 solutions that have been discovered by just training SGD to convergence with different random initializations. So these can be considered to be quite different basins of attractions in many directions. However, we showed that you can actually find subspaces that allow you to walk from one solution to another independently trained solution without really increasing the loss very much along the way. You could never do it with a straight linear path, but you could always do it empirically, it seemed, with a curve as simple as just a polygonal chain with a single turning point. So you walk straight in one direction, turn, walk in another direction, and you end up at the other solution discovered by SGD. And from this perspective, it seems like there aren't even really local optima discovered by SGD. Like, there's these directions where it's very flat, and we should start to think instead about loss valleys rather than single points that might optimize our loss. And this is just an example of another curve. And this is work with Pavel and Timur and Dmitry Vetrov and others. We've kind of continued to sort of explore this work for trying to do efficient Bayesian approximations. This is a visualization recently created by Pavel, Timur, and Javier, again, of this mode connecting curve. Okay. So a bit more specifically, we can consider the actual parameterizations used in these particular figures. So in the top here, we have a polygonal chain. It starts for t equals 0 at one of the SGD solutions, so that's W1 hat. So we started just by finding W1 hat and W2 hat. It ends at W2 hat going to t equals 1. And theta here is what we're trying to learn in discovering this path, and that's related to this turning point here. So theta will live in the same space as W. It will be 30 million dimensional or whatever it is. This is a ResNet 164 on CFAR 100. And here we have an example of a quadratic Bezier curve. Again, moving from one SGD solution to the other by varying t from 0 to 1. Okay, so in order to learn the paths, what we do is we minimize the loss that we use to train the model to find W1 hat and W2 hat uniformly in expectation over the curve. And so what this looks like is sort of a line integral of cross entropy, if we're doing classification, normalized by arc length. And so you can actually imagine that this could be the basis for a new loss function that you might want to use to train your model. Like maybe you actually want to not just minimize cross entropy at a point, but you want to minimize it subject to some constraint, that like the surface integral is greater than or equal to some value at some particular solution. And so this would be one way of trying to incorporate the notion of flatness into your optimization procedure directly. From a Bayesian perspective, we might not want to do that because actually if you integrate your loss surface, then you automatically account for the fact that flat solutions might generalize better because most of your mass will actually be in those wide basins of attraction. Whereas if you start to think about this from an optimization perspective, there's a bit of a rabbit hole because there's this idea, well, I should penalize sharpness, but how much should I penalize sharpness? And so you have to introduce all of these extra hyperparameters, and then there's this question of, can I really rigorously define sharpness? So you can think about it intuitively as like, how much do I increase the loss by walking away from a given solution in a random direction? You could look at the eigenvalues of the Hessian and so on, but then there's this parameterization issue. You could look at Fisher matrices, but any choice is going to have some set of pros and cons, whereas if you're just integrating, all of this stuff kind of resolves itself under the hood. So when we have this loss function, we basically just sample from a uniform distribution and take gradient steps with respect to theta, so a very simple procedure for finding the solutions. Once we found them, we can look at the training error for various different connecting paths. So in red, we basically just have a straight linear path between our two solutions described by t equals 0 and t equals 1, and we can see that the error actually increases almost to 100% along the way. Here we have the Bezier and polygonal chains in green and blue, and we can see that the loss and the training error, the training loss stays very low as we move along the curve. I guess the sort of practical question was then how we can actually use this mode connectivity insight in some kind of application, like what kind of procedure might follow from this discovery that we can walk from one optima to another without increasing the loss. So the first thing that we considered was ensembling. What happens if we just sample points across these paths and then average the predictions of the models associated with those different settings of the parameters. So we have model 1 with some parameter settings. So we have f of x given some setting of parameters w1, let's say. That's for our first optimum. We have f of x associated with some setting of parameters w2. And then we have all of the parameters associated with points along these paths. So those could be f of x wj, and wj is sort of as fine-grained as we want it to be. So we could sample lots of points. And when we sample the points along the curve and average the predictions, we do get better performance. Lower test error in this case, say like 20.5% on CFAR 100, which is pretty good, compared to say 24% on CFAR 100 if we were just to use the solutions at the different points discovered by SGD with random initializations. And this was also important because it meant that these paths existed not due to symmetries in the parameterization. So that might be a cool result, but a little bit deflationary. It's like, okay, there are lots of different settings of the parameters that actually give you the same model, and we all know that about neural nets. But it's not that. Actually, these points correspond to different representations, and that means it actually is going to make a difference to think about these curves from a Bayesian integration perspective or from an ensembling perspective. And this generally led us towards sort of thinking about how we could do efficient ensembling in deep learning. So a little bit separate from the mode connectivity work, but inspired by it in the sense that we discovered that we could actually take very small steps along this path and actually get quite different models. And so the idea here is basically to run SGD with a cyclical learning rate. When the learning rate is high, we're exploring, and as it decreases, we fine-tune a solution, and then we ramp it up and we explore, and then we fine-tune a solution. This is related to snapshot ensembles, except it's much higher frequency. And at the bottom of each cycle, we just average the model associated with that setting of parameters. So we see that the test error kind of is high for high learning rates. It goes down, it jumps up because we're moving to a slightly different part of the loss surface, goes down, and so on. So this was just an efficient idea for ensembling called fast geometric ensembling that was in the mode connectivity paper. And while we were doing this, we were getting in the habit of looking at visualizations of the loss surface and the trajectory of SGD along this loss surface. And we noticed something a little bit funny. So if we visualize the test error rather than, say, the training loss, and we look at the points at the minima of these cycles in this learning rate schedule, they seem to be almost symmetrically oriented around a point of really good generalization. And so this made us wonder whether there was actually something better that we could be doing than model averaging. Can anyone maybe think of an idea here, just looking at this visualization of what we might want to do in order to find a good solution?
Average the solution.
Exactly. So here we're doing this thing where we're adding, f of x1 plus f of x2 plus f of x3 and getting a solution, and f is the neural network with parameters w and inputs x. But in fact, and this is closer to maybe what we might do as a Bayesian, if we think that all these things have basically the same loss, then the Bayesian model average just looks like an equal combination. of these solutions. But instead of averaging F's, maybe we actually just want to average W's. So actually, this is a bit of a non-Bayesian thing to do. But just geometrically, it seemed like it might give us good performance. If we take the average of W1 plus W2 plus W3, then we might find a good point of generalization. And when we do that, we indeed found that these points generalized very well, and we called this procedure stochastic weight averaging. So the next question is, why does this lead to a point of good generalization? So I'll get into that in a moment. First, I'll just briefly describe the procedure in a little bit more detail. So the idea is we start with a standard learning rate that one might use to train a ResNet on CFAR. And then we decrease, just as usual, but we decrease to a higher learning rate than one might normally do if they were training with SGD. And then we start the cyclical schedule, and we average the parameters at the minima of these cycles, update batch norm, and that gives us our solution for our weights that we want to use. A simpler variant of this is basically just to decrease to a relatively high constant learning rate, and then just average the points as we proceed. So every epoch, or we could even do it within epochs. So any questions about this stochastic weight averaging procedure, just how it works? So it's just running a single chain of SGD with a modified learning rate schedule, and we're averaging the points that are being traversed by SGD after a sufficient burn-in period.
That was just one model, one set of weights.
Just a single model. So that's a difference from this fast geometric ensembling procedure I described, where you actually have a bunch of models. So we can see immediately that we benefit from this computationally, because instead of having at test time to use K models, which will slow down our prediction time K times, we just have a single model. So this is just as fast as kind of training with SGD. Okay, yeah.
So regardless of whether you use a cyclic or constant learning, well, I guess in the case of a cyclic learning rate, you can have parameters that sort of lost and get slightly worse. Did you also try to simulate a milling approach, and rather than vary the learning rate over many steps, just have a constant decay of it and accept gradually less worse loss?
We didn't do that, I believe. We experimented mostly with cyclical rates and kind of plateauing at a relatively high constant learning rate. We did consider things like maybe trying to weight the average in some way by the loss rather than just taking an equal average. But it seemed that an equal average was very simple, and it was already giving us a boost over standard SGD, quite a big boost, like about a 30% reduction in relative error. So we mostly just stuck to these very simple schedules. But this is a good idea, and it's also a good point that we don't even need to do this with SGD. We could do it with Atom or all sorts of optimization procedures. And the really key insight here is that we want to modify the learning rate schedule, and we don't want to take an exponential moving average. So in convex optimization, there's this thing called Polyak averaging, and it's typically an exponential moving average with a decaying learning rate. And so that actually won't change your final solution very much. It smooths the trajectory of SGD, but the solution, especially in deep learning, has fairly similar properties. And that's more about rates of convergence rather than generalization. And we'll see why the modified learning rate and the equal average are important just in a moment. Mm-hmm.
Is there a link between this and this paper where they use the runtime, like test time drop-off?
Test time dropouts. I'll get to that in a moment. Yep. Okay. So, we wanted to understand why taking this equal average of parameters was giving us better generalization. So, if we look in test and we run, so we train as usual up to epoch 125 with SGD and a regular learning rate schedule. This is ResNet 164 on CFAR 100, and then we keep sort of training to convergence. In test, we see that SGD moves to the periphery of a good solution, whereas if we start doing the equal average after epoch 125 up to about epoch 200, where we would normally truncate our procedure, we move to a point of very good generalization. However, in test, it's exactly the opposite. So we actually see an empirical realization of this horizontal shift between the training and test loss. In train here, SGD is actually centered on a relatively good solution, and SWA is on the periphery of a set of good solutions. And so, this also, led us to sort of question, why it is that SWA is actually finding better generalization in test, but not necessarily the best value of the loss in train. In fact, regular SGD training might find a slightly better value of the loss than this stochastic weight averaging procedure. Okay. So, there was this connection with width and generalization. This is one thing we could do to try to begin to understand why the weight average solutions were providing better generalization. So what we've done here is sample a bunch of random direction vectors uniformly on the surface of a unit sphere. And we've walked away from each of the SGD solution in green and the SWA solution in blue along each of these curves. And what we found is that we needed to walk much, much further from the SWA solution to increase the test error by the same amount than if we walked away from the SGD solution. So this suggests that in random directions, that SWA is finding a much flatter solution. We can also look at particular directions, so it's interesting to think about the direction that actually connects the SGD solution to the SWA solution. So in green, we have the training loss along that direction, and the origin here starts at the SWA solution. So we can see that actually SGD is finding a better value of the loss than SWA. SGD with this green square and SWA with this green circle here. But in test, in blue, SWA is again sort of centered on a region of high-performing solutions, and it achieves much lower test error than SGD, which is now not performing so well. An interesting thing to note here is that even on the train surface here, though SGD is finding a better sort of solution according to the training loss, it's near the periphery of very sharp ascent, whereas the SWA solution is actually in quite a flat region of the loss. And this seems to be very important in order to achieve better generalization performance. Another perspective is to actually see this procedure where we're averaging the weights as an approximation to what we were doing before, where we were averaging the models. So recall when I mentioned this fast geometric ensembling procedure, we had a very high frequency cyclical learning rate. So we were taking very small steps in weight space. So in that case, we can reasonably do a linearization of the model and argue that actually averaging the weights is going to approximate an ensemble of the models if we average the models associated with those weights. And in fact, our function that uses this SWA solution is much closer to the average of the functions with the individual weights that we use to form the SWA average than it is to maybe the individual functions in this sum. That's another perspective. I'll do one more perspective first before results. Recall that the loss surfaces are extremely high dimensional. And there's some interesting theory showing that if we run SGD with certain learning rate schedules, we're approximately sampling from a Gaussian distribution in one of the basins of attraction centered on one of the local optima. And so this means that SGD is actually going to be traversing the surface of this hypersphere because most of the mass of a high-dimensional Gaussian distribution is actually in a very thin shell that we can visualize as a soap bubble here. This is from a blog post by Ferenc Uzar. This will be out at radius root d. So this is kind of a fun exercise if you are sampling from a Gaussian distribution and visualizing the norms of these samples. As you increase the dimension, eventually all of them will be concentrated at root d. And this is because even though the density is highest in the center, mass is density times volume, and in high dimensions, the volume blows up very quickly as you increase the radius. And so this is described by a chi distribution. And we have basically SGD moving along the surface of this soap bubble, and by averaging the points, we get to move inside the bubble. And so we can imagine that there are a bunch of different solutions, sort of some kind of loss valley, that all incur fairly low loss. SGD moves along, regular SGD, and just converges to the boundary of this set of high-performing points. There isn't much of a gradient signal to actually go inside. Whereas this modified procedure ramps up the learning rate and starts spinning around this set of high-performing points. And by averaging the points on this trajectory, we get to move inside and have a much more centered solution, which will be flatter. And this is not something that would be discovered by a standard optimization procedure. There wouldn't be any incentive to actually move inside.
Can you explain again why there is no gradient pushing the SGD solution towards the center?
So all of these points have similar values of loss. So there's no, it's very flat. So SGD is not going to be very motivated. Once it finds a solution with zero loss, it's kind of done. It doesn't really need to move inside that set. There is an argument, I mean, there's the whole mini-batch SGD argument. SGD finds flatter optima than BFGS. This is partly helped by things like gradient noise that you get from mini-batching. But in practice, SGD is still finding relatively sharp optima compared to what we could be finding. So I think it's a little bit misleading to simply say SGD finds flat optima and BFGS finds sharp optima. In fact, both are finding kind of sharp optima. And even to refer to them as optima might be a little bit misleading. In fact, all of them could be in some proximity of some basin of attraction if they start off with the same initializations. It's just that different procedures are moving inside to different extents. So when a model sort of finds a sharp optima, it could be that it just is near the very edge of a set of high-performing points. And it seems like there really are these loss values rather than just very individual points that achieve good values of loss with neural nets. And Tom Goldstein's group has this very interesting recent paper sort of understanding generalization through visualizations. And he's arguing that in this case, we actually have sort of a blessing of dimensionality. And so a lot of optimization procedures are helped by the fact that you have a high dimensional space because the volume of these wide basins of attractions will be much greater in that case than the volume of the sharp basins of attraction. And so a lot of optimization procedures will be biased towards finding somewhat wide solutions, but we can actually do a lot better by using things like stochastic weight averaging. Okay, so in this figure here, what we've done is we've run our procedure with a very high constant learning rate. And the test error is shown in green, so we can see that it's hovering around 35% for CFAR 100, which is not great. 20% is sort of a good value of test error on this problem. In blue, we see the error according to a standard learning rate schedule, converging to about 19% error or so. In red is what we get if we start averaging at epoch 145. So we see that actually the test error shoots down very quickly and to a value that's less than what we get with the standard learning rate schedule. So this suggests that there actually, in addition to finding points of better generalization, I think there could be interesting future work in trying to understand exactly when to start averaging and so on in order to also achieve good rates of convergence. Okay, so in summary, stochastic weight averaging is this simple procedure that can really be used as a drop-in replacement for SGD or other optimizers. It's not so specific to SGD, so you can do a similar thing with Atom or whatever your favorite procedure is for a given problem. There isn't really any runtime overhead. There's a very minor sort of few percent memory overhead. This is now natively implemented in PyTorch contrib. So trying it is as simple as just calling optim.swa instead of optim.sgd. And you can start from a pre-trained model. So you may not want to train your whole model from scratch again. In that case, you just sort of load up what you get from regular SGD pre-training, increase the learning rate, and start taking an equal average for about 10 or so epochs, and you'll see an improvement in relative error. And these are the tables I quickly skipped. So basically, we consider a load of different models, SGD training as prescribed by the authors of the papers for these models, this fast geometric ensembling procedure, and what we get if we run stochastic weight averaging with the same computational budget as we're allowed for SGD, as well as what happens if we run it for a little bit longer. And so with the same budget, we see sort of a 20 to 30% relative decrease in error over SGD training, essentially for free. If we keep running, we actually can find a slightly flatter solution. And this will help us further with generalization up to about 1.5 computational budgets. And this is something we also saw with ImageNet. And since this work, which appeared last year at UAI, there have been a number of papers considering this procedure with other types of networks, not just convolutional nets, and in other contexts, not just for computer vision applications. Okay. So the next question is how we can use some of these geometric insights for fast Bayesian inference procedures. So with stochastic weight averaging, we basically are just computing the first moment of the SGD iterates with this modified learning rate schedule. A natural extension would be to compute also an approximation to the second moment of these SGD iterates, and then use that as a Gaussian approximation as our for our posterior distribution over parameters. So I mentioned a while back there's some theory saying that if you run SGD with certain learning rate schedules, you're eventually sampling from a Gaussian distribution. So the intuition is, instead of using SGD to sample from a Gaussian distribution, why not just characterize that Gaussian distribution directly and then use that in your approximate Bayesian model averaging procedure. So we compute approximations to the statistics of the SGD trajectory. This gives us a Gaussian approximation to the posterior, P of W given D. Once we have that, we can sample from that directly and compute our Bayesian model average. Even though the theory suggests that this could capture the shape of the posterior, it makes a lot of assumptions that might be questionable in practice. So we wanted to verify this by actually trying to visualize the loss surface along the principal components of the SGD iterates. So we could see actually what SGD was doing in this space and how it related to the loss surface in this space. And it did seem to be actually capturing the loss surface quite effectively. And we tested this on a bunch of calibration problems. So here, on the vertical axis, we have confidence minus accuracy. Confidence is the highest output of our softmax for classification. And ideally, the difference would be 0. That would be for a well-calibrated model. This would allow us to kind of faithfully interpret the outputs of our ConvNet as probabilities of class labels. In green, we have standard SGD training here. In blue, we have this SWA Gaussian procedure, or SWAG for short. And we see that it achieves much better calibration and really without much computational expense. This is a very fast thing to do. It works better than MC dropout, which is a standard sort of procedure. Someone mentioned like doing dropout at test time and ensembling to get predictions. It has advantages over other non-Bayesian sort of approaches like temperature scaling, especially in things like domain adaptation, where with temperature scaling, you would actually want to use your target data to calibrate the value of the temperature. And this is something that you can't really do if you don't have access to the target data. So in this case, actually representing epistemic uncertainty properly in the data that we are given will still help us in these transfer learning tasks. As you can see, there's still overconfidence. So if we're above this curve, that means that confidence is actually higher than the accuracy associated with that confidence. But it's doing a lot better than standard SGD training and a number of these alternatives in other colors. We can also look at test likelihoods for all sorts of different problems. And again, we found that the SWAG procedure generally performed best and often better than MC dropout and always better than just standard SGD training. We also saw that just doing regular SWA averaging helped a little bit with calibration and some of these things. Okay, so in order to justify the SWA procedure, we were looking at visualizations of the loss surface in the space of principal components of the SGD iterates. And this gave rise to the idea that maybe instead of doing inference in the original space, we could be doing inference directly in some kind of subspace. And so the idea here is construct a subspace for a given network that has a high dimensional parameter space, perform inference in that subspace, and then basically we just sample from our approximate posterior in the subspace, and then we convert those samples into our original space again and do our Bayesian model average. And so we found that in following this procedure, we could actually approximate the posterior of a wide ResNet that has 36 million parameters, even in a 5-dimensional subspace, and achieve kind of very good results. So the intuition is that even though the parameter space is extremely high dimensional, a lot of the interesting variability of the function could be captured in a really low dimensional subspace. And so the basic idea is we have our original parameterization W. It's equal to some linear projection times a low-dimensional vector Z plus some kind of offset. And our goal is to construct P and then do inference in Z space. And then once we've inferred the posterior over Z, we can sample from that and use this equation to get our W's. So we start just by centering this linear subspace around a good solution. So W hat, for example, could represent the SGD trained model, or as we did, sort of the stochastic weight average solution. And so this means even if we use a random linear projection, we're already starting in a good place. So this means that we could have like a very vague prior, for example, over Z here, and we would still be covering a good region of the loss surface. And when we do that, when we have a random subspace, we find that we can actually get better point predictions, although the uncertainty, if we visualize this approach in regression, isn't necessarily so intuitive. So we don't see that the predictive distribution is getting broader, for example, as we move away from the data, as we might want to, because there ought to be more functions that are consistent with our observations away from the data than near the data. The next approach was exactly what I mentioned, where we used actually just the principal components of the SGD trajectory to construct this P matrix. So we just do a singular value decomposition on those sort of iterates subtracted by the W hat solution. And here we actually find a much better subspace. We get even better predictions, and we get more intuitive-looking predictive distributions. And actually, at the beginning of Polina and Pavel's talk, I heard someone say, oh, it looks like there's a Gaussian process on the first slide. The twist is that wasn't really a Gaussian process. That was actually a neural net. So we can get GP-like sort of quality predictive uncertainties, even in the regression context, which has really been a challenge. And we can even do inference in this mode-connecting subspace. This would be a very unusual-looking subspace, and we can get even better predictive distributions. The drawback of this approach is it requires forming the subspace first, which does incur some computational expense. You need to train at least 2 models and then find the connecting path, whereas with the PCA subspace, you can do things very efficiently. And here we have an animation, basically, of the different functions that we get that fit this data as we move along this mode-connecting subspace. So you can see in pink here, basically this is the neural network corresponding to the parameter space given by this pink circle on the right panel. And so this really emphasizes that there's a lot of functional diversity in this mode-connecting subspace. It's really not due to symmetries in the parameterization. We get very different looking models corresponding to these different weights. It's also suggestive that maybe we should be thinking a little bit more in function space than in weight space, because really it's not the number of parameters that we care about compared to the number of data points. It's the distribution of support in the sort of space of solutions that we really want to think about in terms of generalization. And that really connects back to one of the early slides when I was arguing that we want to consider very complicated models. In a sense, it doesn't matter if we have 1 million parameters or even an infinite number of parameters as we would with a non-parametric model. What matters is the sort of support that we have over different solutions for the data and whether they're representative of the types of models that we might want to use for that particular problem. Just as a contrast, we can also look at the predictive distribution that we get from standard variational inference, and we can again see that it's not doing a great job of capturing variability in the function or epistemic uncertainty, kind of moving away from the data. We're not getting very much increased uncertainty. And so I think sometimes just looking at tables of numbers on UCI of likelihoods can be a bit misleading, because this can actually ignore the fact sometimes that we might want increasing uncertainty and things like this away from the data. So it's always good as a sanity check, I think, to try to make these kinds of visualizations to see if the uncertainty really is reasonable for your model. So here we have a summary of the different subspaces we considered and the different predictive distributions associated with those subspaces.
When you say support, is that sort of intuitive or density? Because in a lot of these models, like every function is actually in the support, right? Or every function within some regularity class can be represented.
Mm-hmm. So what I mean is kind of the distribution of support. So in this plot where we had all possible data sets on the horizontal axis, so every point here is just a different data set, and we have the evidence on the vertical axis, which is the probability that we would sample that data set if we were to randomly sample from the parameters, condition on those parameters, and sort of draw our function. The sort of support I'm talking about is how that's sort of distributed. So I would say that, in a sense, fully connected nets are the most flexible neural network, but conv nets actually do better on a lot of vision problems, and they achieve that by restricting the support of the model and kind of squashing it towards, this more constrained set of data sets that might be representative of vision problems and might sort of capture various invariance properties. I would argue from a fully Bayesian perspective, this isn't quite what you would want to do. Instead, you might want a soft inductive bias that would sort of push your prior likelihoods around those types of solutions, but wouldn't constrain other solutions that you actually believe could be representative of that problem. And from this perspective, I mean, you could have 1 trillion parameters. If you all add them together, you can only create one data set, or like, very simple sort of solutions. So, what you do with those parameters in conjunction with the functional form of the model is really what matters, not how many parameters you have exactly. And there's all this recent work on the neural tangent kernel and so on, which is related to actually taking infinite limits of neural nets, which is something people actually have been doing for decades. And these involve, an infinite number of parameters and can still generalize well. So here we have NLL and accuracy numbers using SGD in each of these 3 subspaces. So this also emphasizes that, Bayesian methods aren't just achieving better calibration, they're actually getting better point predictions. So in the random subspace, we see about 1.5% increase in accuracy on CFAR 100. Using the PCA subspace, we see a further increase in accuracy. Using the curve subspace, we see a further increase in accuracy. So we can actually use these methods for better point predictions. So very briefly, we've considered a number of other applications where it might be particularly exciting to try to reason about loss geometry to find solutions which will generalize better. One of these has been semi-supervised learning, where we want to share structure across the unlabeled points in gray shade here and the labeled points in black and white in order to, say, have a more informative decision boundary. In these cases, you don't actually have a lot of information signal from the labeled set, so you have these particularly flat regions of the loss surface. And when the loss surface is poorly defined, that's when you'll benefit most from things like averaging. That's when a central solution will be really important. If you think about a simple model like logistic regression, having a lot of data, your posterior will be really collapsed anyway. So having like a centered solution isn't even really, an interesting concept. Whereas in deep learning, it can be very significant, and it can be especially significant in things like semi-supervised learning. And using these ideas, we managed to get the best performance out there on all sorts of semi-supervised benchmark problems. For example, achieving almost the same level of performance with like 5% of the data on CFAR 10 as if you had all of the data points with a gold standard neural net. We also looked at doing training in low precision using loss geometry. This is, again, kind of intuitive. So this is work with Polina, Guandao, Tianyi, Krista Sa, and Zhan Bai. And the idea there, intuitively, is that if we have a very flat region of the loss surface, then quantizing shouldn't really hurt us. What we do is we run SGD in low precision with a high learning rate. And these are the representable points on this grid in that level of quantization. And then in high precision, we take an average, and that we use that as our solution. And we found that actually we could go all the way down to representing all numbers, including gradient accumulators in 8 bits, and get as good performance as full precision SGD on CFAR 10 and CFAR 100. So this is sort of maybe a result that could become even more significant in the future as we develop sort of hardware that is specifically accelerated for low precision computation. So in conclusion, by considering the geometry of loss surfaces, we can make much more effective procedures for scalable Bayesian model averaging. We basically just recycle a lot of the information that we would get from SGD training already to do better, both in terms of calibration and in terms of the accuracy of our point predictions. From a purely optimization perspective, we can sort of start to understand some of the properties that have historically been a bit mysterious in deep learning. I think the future directions really involve thinking more directly in function space. So for example, in the subspace procedure with PCA, we're using weight space diversity as a proxy for function space diversity, which is what we want if we do this Bayesian model average. But maybe there's a more direct way to think in function space. And this is what happens often with Gaussian processes. So in tomorrow's sort of deep learning seminar, we'll also talk about Gaussian process approaches and connections with things like neural tangent kernels and infinite limits. And quite often you can combine the best of these worlds such that you have a model with extremely broad support that is essentially universal approximator, but it has a lot of inductive biases given by the neural network, and you can do efficient computation through developing approaches in numerical linear algebra, Krylov subspace methods that can be very effectively parallelized on GPU computing hardware. All right, thank you.